Introduction to Arrhenius Equation. Let's start with a question. Is sugar easily soluble in hot water, or cold water? Hot water. Is it not? Do you know why? This is because hot water has more energy than cold water. So, sugar dissolves faster in hot water than in cold water. We can say dissolving sugar in water is a chemical reaction. Because here, two different things or two reactants combine to form a new chemical product. As this chemical reaction is accelerated by temperature, we can say that the increase in temperature accelerates a chemical reaction. This applies to all kinds of chemical reactions. And the temperature dependence of the rate of a chemical reaction was first proposed by the Dutch chemist Jacobus Henricus van 't Hoff in the year 1884. And the equation that relates the temperature dependence of the rate of a chemical reaction is called the Arrhenius equation. In this lesson, we will discuss Arrhenius equation in detail, and at the end of this lesson, you will be able to explain the temperature dependence of a reaction through the Arrhenius equation. Arrhenius equation. For a chemical reaction, if the temperature is increased by 10 degrees Celsius, the rate constant, or the rate of a chemical reaction is nearly doubled. Let's start with some examples of the temperature dependence of the rate of a chemical reaction. In a mixture of potassium permanganate and oxalic acid, the potassium permanganate gets decolorized faster at a higher temperature than at a lower temperature. Let's see another example. At 0 degrees Celsius, nitrogen pentoxide takes 10 days to decompose, half of its original amount. But, at 25 degrees Celsius, nitrogen pentoxide takes only 5 hours, for the same amount of decomposition. And, at 50 degrees Celsius, nitrogen pentoxide takes only 12 minutes, for the same amount of decomposition. As said in the introduction part, the temperature dependence of the rate of a chemical reaction is expressed through the Arrhenius equation. And it is expressed as K is equal to E to the power minus EA by RT. It provides the relationship between the rate constant of a chemical reaction, the absolute temperature, and the A factor, also known as the pre-exponential factor. Where EA is the Arrhenius factor or the frequency factor, K is the rate constant, R is the gas constant, EA is the activation energy in joules per mole, and T is the temperature in Kelvin. Let us consider the reaction of hydrogen and iodine to form hydrogen iodide. During the reaction, a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate called the active complex. They exist in this intermediate state for a very short time. The energy needed for this intermediate state is called the activation energy EA, expressed in joules per mole. Then this intermediate state breaks up to form two molecules of hydrogen iodide. In this graph, the reaction coordinate represents the profile of energy change when reactants change into products. Decomposition reactions are always an endothermic process, which means there will be the release of energy. And the final energy of the reaction depends upon the nature of the reactants and products. To predict the behavior of molecules in a chemical reaction, Ludwig Boltzmann and James Clerk Maxwell used statistics by plotting the fraction of molecules, that is, Ne divided by Nt, with a given kinetic energy, E versus the kinetic energy. Here, Ne refers to the number of molecules, with energy E, and Nt refers to the total number of molecules. The peak of the curve indicates the most probable kinetic energy, which is the kinetic energy of the maximum fraction of molecules. When the temperature increases, the average molecular speed will increase, and the peak of the curve will shift to the right. You can see, when the peak shifts to the right, the height of the graph decreases. And the area under all three curves will be the same. This shaded portion indicates that, when the temperature is increased to T plus 10, a fraction of additional molecules collides with energies greater than the activation energy. And the rate of chemical reaction will get doubled with 10 degrees increase in temperature. By taking the natural logarithm on both the sides of the Arrhenius expression, we get natural log K is equal to minus EA by RT plus natural log EA. We get a straight line when we plot a graph for natural log K versus 1 by T. This tells that increasing the temperature or decreasing the activation energy will increase the rate of the reaction, and an exponential increase in the rate constant. In this graph, the slope is minus EA by R, and the intercept is natural log EA. Using this, we can calculate the values of EA and EA. At temperature T1, the second equation becomes natural log K1 is equal to minus EA by RT1 plus natural log EA. At temperature T2, the second equation becomes natural log K2 is equal to minus EA by RT2 plus natural log EA. Subtracting equation 4 from 3, we get that natural log K2 minus log K1 equals EA by RT1 minus EA by RT2, which can be written as natural log K2 by K1 is equal to EA by R into 1 by T1 minus 1 by T2. Converting this equation to log, we get log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2, which can be written as log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 T2. This is the Arrhenius equation, used to calculate the effective temperature on the rate of a chemical reaction. Conclusion? Thus we learnt that an increase in temperature accelerates a chemical reaction. And for a chemical reaction, if the temperature is increased by 10 degrees Celsius, the rate constant, or the rate of a chemical reaction, is nearly doubled. The equation that relates the temperature dependence of the rate of a chemical reaction is called the Arrhenius equation. Summary. From this lesson, you have learnt that for a chemical reaction, if the temperature is increased by 10 degrees Celsius, the rate constant, or the rate of a chemical reaction is nearly doubled. The equation that relates the temperature dependence of the rate of a chemical reaction is called the Arrhenius equation. To predict the behavior of molecules in a chemical reaction, Ludwig Boltzmann and James Clerk Maxwell used statistics by plotting the fraction of molecules, that is, Ne divided by Nt, with a given kinetic energy E, versus the kinetic energy. And the Arrhenius equation can be expressed as log K2 by K1 is equal to EA by 2.303 R into T2 minus T1 by T1 T2.